Okay, we're trying to get a handle on how the local behavior, the behavior of a vector function in the plane, determines the global behavior as stated by Green's theorem. Global behavior relating the integral around a boundary of a region to the integral of some partial derivatives within the region over the area. It's really a very astounding result. Okay, so we're kind of stuck down here and trying to develop a theorem that's not quite the same as any theorem I've seen. Trying to approach it in a way that somebody who was trying to figure this out, trying to get a handle, seeing I think there's something there, the numbers work out, can I really make this rigorous? Okay, trying to sort of model the way a mathematician will work through a problem that hasn't yet been solved. Again, we have a very facile proof using the fundamental theorem of algebra of Green's theorem, but that's a global theorem. Now it ultimately depends on the fundamental theorem of algebra, which goes local to global, but don't want to rely just on that theorem. I mean, that's a great way to prove the theorem. It works, but it doesn't give you the insight about the local behavior. You can take the global and conclude the local behavior, but how do you build from local to global? And that's what we want to do here. Okay, so we've done quite a bit with it. So just moving again, kind of in the spirit of mathematical research. I've sketched this picture with a sample point, x star, y star. I know I'm going to want to use a sample point. Okay, I know that to do a rigorous proof that goes local to global, I've got to use sample points. I've got to use partitions of some kind and sample points. So using that intuition, I've got a sample point here, but I haven't yet figured out exactly what to do with it. Okay, so I'm getting my notation a little bit confused here. Now, I make a statement here. Now again, looking at the n function, the reason the integral here is not equal and opposite to the integral over here, the integral of the n function over this path minus the integral, well, plus the integral over this path, which is the integral of the difference of the n function between here and here. Okay, well, the difference of the n function between a point here and here, where you have the same y value, just depends on the x derivative, because x changes from here to here. It's the rate of change with respect to x between here and here that determines the difference in the values. So, what is the difference in the values? Well, I originally made a statement didn't have stars on the y's, so ignore the stars on the y's for a minute, and then I'll talk about why I put the stars on the y's and why that might or might not have been a wise thing to do. N of x naught plus delta x y minus n of x naught y has to be approximately equal to nx of x naught y times delta x. For any given y value. Okay, and why is that? Well, because by definition of the partial derivative, nx of x naught y is the limit as delta x goes to 0 of this expression here, I'm not going to read it to you, divided by delta x, the rate of change definition, the definition of the derivative definition. So that if you multiply this by delta x, in the limit as delta x goes to 0, this minus this is nx of x naught y times delta x. That's for any y, for any given y. So if I want to use this y, I can make that statement. If I want to use this y down here, I can make that statement. Now, I decided to just call it, to do this in terms of y star. So now I'm not using the y up here or the y down here. I'm using the y right here, the y value. And why did I decide to use that? I decided to use that because if you make this region small enough by the continuity of the second derivative and so forth, if you make delta y small enough, it doesn't make much difference. And in the limit as delta y approaches 0, it doesn't make any difference at all. Okay, the difference kind of evaporates, but we don't want to wave our hands about evaporation. We're going to want to make this rigorous. So I've made this statement. And this statement, we can kind of take as a tentatively good statement, although I haven't proven that it doesn't matter if you use y star. I just said how you prove it, but I haven't written out that proof, so I might be, deluding myself at this point. I might be down a wrong path. Okay, well, I come down here, and I then write that the integral from y naught to y naught plus delta y of n of x naught plus delta x y minus n of x naught y. Now what's that? Well, the integral from y naught to y plus delta y of n of x naught plus delta x y is just the integral over this part of the path minus this, and actually minus this is the integral over this path. You're integrating the difference between here and here. Okay. So for any y between y naught and y naught plus delta y, you talk about the difference along the line where y is constant, where y has this constant value. And that, of course, is, as we've seen before, this part of the integral over this part of the path plus the integral over this part of the path, because the integral over this part of the path is the negative of the integral that you would get if you went this way. Okay, I don't want to talk too much about that right now. So what I've said then is that this has got to then be approximately equal to, well, this is approximately equal to this. It's got to be approximately equal to this. Okay? And then this, in turn, is approximately equal to this, because if delta y is small and the function is nicely behaved and the second derivative continuous, if delta y is small enough, then nx of, well, actually I don't even have to say if y is small enough, okay? If I've got my y star here, it's fixed, so this nx of x naught y star delta x is constant. So if you integrate a constant over an interval of length delta y with respect to y, you just get that constant times delta y. Okay, so, and that's why I wanted to put the y star there. But I still got that x naught. Now I can make the totally analogous statements about the m function, okay? And I've done that, and I'm not going to read it to you, but I'm just using the fact that the partial derivative is defined as it is, and that this is equal to my times x star y naught, and then I make a statement about this integral here, and you can deconstruct this. I'm not going to, I want you to think it through. Understand what I did here, and now I've got this expression, and I've got an x star y naught. Okay? I really don't want x star y naught or x naught y star. I want x star y star here, and I want x star y star here. And it isn't that hard to get it. But then, what do we have? This is integral of n over first part of the path, we'll say with respect to y, plus the integral of n with respect to y, and it's not the first, it's the second, this is the second. Okay. Part 2 of the path and part 4 of the path. So it should be clear that what we have here is the integral of the second part and the integral over the fourth part. And it's the integral of the entire function, because there's no change in x between here and here. And only the y component of the function is integrated with respect to this path, so that's what we have. So, and what we have here is the integral over path 1 of m dx minus the integral over part 3 of m dx. And actually I've got it wrong. It's the integral over part 3 minus the integral over part 1, because part 3 is where y is equal to y naught plus delta y. So I've got the sign wrong, so I can say it's, well, I can say it's a negative. Okay, it's this. Okay. So the integral around here of your f of x, y, your path integral over, and it's a dot product. Is the integral of m dx plus n dy, which is equal to this, well, the negative of this plus this. And now I've got a problem with that negative sign. Anyhow, yeah, I'm troubled by a negative sign here. I'm not going to worry about it on screen here. I'll figure it out. Something bothers me, and it should. That's right, that's right, that's right. Oh, yeah. Okay. And this is supposed to be equal to this minus this. Actually, this plus this. And it is. Okay. And when we put these together, we have my of x star y naught delta x plus nx of x naught y star delta x delta y. Well, it'd be, that should be minus this. Yeah, it's all messed up. But if you look at this, if it's this minus this, then this is the integral of nx over the area. This is the integral of my over the area. Because nx doesn't change much, if nx is almost constant, you just multiply it by the area. If my is nearly constant, you just multiply it by the area. So for small areas it works. But, as I say, we're still waving hands. And I screwed up a sign there, but that's easy to fix. Okay, so here's our idea. Now next I want to use some limits and then pose a question that hopefully lead you to complete the proof.